In 1a, we are asked to find the first four terms in ascending powers of x of the binomial expansion of a quarter minus 5x raised to the power of a half, giving each coefficient in its simplest form. So we're looking at 1 over 4 minus 5x raised to the power of a half. I will factor out the quarter and it will inherit the power of a half, and within the bracket we've got 1 minus 20x raised to the power of a half. If you ignore the powers of a half, then a quarter times 1 is the quarter we had here, and a quarter times the negative 20x is the minus 5x we had here. We are always trying to attain a form of 1 plus or minus something in terms of x, and therefore I can proceed with the binomial expansion. So a quarter to the power of a half is simply a half, and then we've got 1 plus the power of a half times negative 20x plus the power of a half times minus a half, deducting 1 from the power, over 2 factorial times minus 20x all squared plus a half times minus a half times minus 3 over 2 divided by 3 factorial times minus 20x raised to the power of 3 plus dot dot dot. I will proceed by simplifying within the brackets. We've got a half, and then it's 1 minus 10x minus 50x squared minus 500x cubed plus dot dot dot. And upon further expanding, we get a half minus 5x minus 25x squared minus 250x cubed plus dot dot dot. In part B, we are asked to substitute x is 1 over 100 into the answer we got for A to find an approximation for root 5. Giving our answer in the form A over B, where both A and B are integers to be found. So let's start by substituting x is 1 over 100. This leads to a quarter minus 5 times 1 over 100 and all raised to the power of a half. If we plug this on the calculator, we get an answer of root 5 over 5. This means that if I substitute x to be 1 over 100 in this expression here, then I'll be obtaining an approximation for root 5 over 5. So this is approximately a half minus 5 times 1 over 100 minus 25 times 1 over 100 squared minus 250 times 1 over 100 cubed, and therefore we arrive at root 5 over 5 being approximately 1789 over 4000, and if I cross multiply, I get root 5 to be approximately 1789 over 800. That's my answer for the approximation of root 5. Now, alternatively, someone could recognize the root 5 over 5 as simply being 1 over root 5, which means that 1 over root 5 is approximately the 1789 over 4000, and I can simply flip both sides to arrive at root 5 being approximately 4000 over 1789, and both of these answers are acceptable to claim both marks of this part of the question. In question 2, we're given a sketch of the parallelogram ABCD. We're given the vector AB and the vector BC, and we are asked to find the size of the angle ABC in degrees to 2 decimal places. So we're trying to find the angle here. So standing at B, we will be considering the vector BC and the vector BA. Notice that we need both arrows to be pointing outwards so that we've got this angle here to be found, and I'll be considering the dot product of BA and BC. So we've got BA dot BC, which is equal to the magnitude of BA times the magnitude of BC times cos theta, which is the angle we're trying to find. Now the vector BA is simply the opposite of AB, so it's going to be negative 6, 2, negative 3. The vector BC is given to be 2, 5, 8, and the magnitude of BA will be negative 6 squared plus 2 squared plus negative 3 squared and all square rooted. The magnitude of the vector BC will be 2 squared plus 5 squared plus 8 squared square rooted, and then it's the cos theta term. Now when we do the dot product of two vectors, we do I times I plus j times j plus k times k, and this leads to negative 12 plus 10 minus 24 being equal to 7, which is the magnitude of BA. It's the result of this here. And the magnitude of BC turns out to be root of 93. So we've got 7 root 93 cos theta, leading to negative 26 is 7 root 93 cos theta, and therefore negative 26 over 7 root 93 is equal to cos theta. If we do shift cos of the left-hand side and we are in degree mode, we get an answer of 112.65 degrees. In part B, we need to find the area of the parallelogram ABCD, giving our answer to 1 decimal place. So this is the parallelogram. Let me add the information we have found up to now. We've got the magnitude of BC to be root 93. We've got the magnitude of BA to be 7. We've got the angle here, 112.65 degrees. I could draw the diagonal from A to C, and if I find the area of this triangle here, I just need to double it, and that will give me the area of the parallelogram. So the area of the parallelogram ABCD will be given by twice the area of the triangle, which is a half AB sine C. So a half times the 7 times the root of 93 times the sine of 112.65 ... I'm using full accuracy here, and this gives an answer of 62.3 units square for the area of the parallelogram. In question 2, we're asked to prove by contradiction that there is no greatest odd integer. This is only worth 2 marks. It's the simplest contradiction you could be asked. So the proposition says that there exists no greatest odd integer. We will always start by assuming the opposite of what we need to prove, and the negation of the statement there exists no greatest odd integer is simply that there exists a greatest odd integer, which I will call n. So if we just consider n plus 2, what we know for n plus 2 is that it is certainly odd because it is 2 more than n, where n was odd. So n plus 2 is an odd integer, and certainly n plus 2 is greater than n. This violates the fact that n was the greatest odd integer that existed. So this is a contradiction, and we conclude that there exists no greatest odd integer. In question 4, we've got the curve C defined parametrically. The parameter t attains values greater than 0, and we need to show that the equation can be written in this form, where x is greater than k, with a, b, c, d, and k being integers to be found. Well, I will start by stating the parametric equations for x and y. I'll be making t the subject for each of these. So for x is 1 over t plus 2. I will start by saying that x minus 2 is equal to 1 over t. And if I take the reciprocal of both sides, I arrive at 1 over x minus 2 being equal to t. Now for y being 1 minus 2t over 3 plus t, I will start by cross multiplying. So y times 3 plus t is 1 minus 2t, leading to 3y plus yt is equal to 1 minus 2t. I will collect the terms containing t on the left-hand side. So we've got yt plus 2t is equal to 1 minus 3y. I will factor out the t, so t brackets y plus 2 is 1 minus 3y, leading to t is 1 minus 3y over y plus 2. And I can now simply equate the two expressions that we have found to be equal to t. So we are looking at 1 over x minus 2 being equal to 1 minus 3y over y plus 2. Remember, I'm trying to make y the subject here, so I will start by cross multiplying. We get y plus 2 is equal to 1 minus 3y times x minus 2. So y plus 2 is equal to x minus 2 minus 3yx plus 6y. I will be collecting the terms containing y on the left-hand side. So we've got 3yx minus 5y is equal to x minus 4. And then I will be factoring out the y, leading to y brackets 3x minus 5 is equal to x minus 4. And therefore y is x minus 4 over 3x minus 5. In addition, we need to find the domain, the value for k, for which x is greater than k. I will start by the fact that t, the parameter, was attaining positive values, so t was greater than 0, which means that 1 over t is greater than 0 because 1 divided by any positive number is also positive. Now if I add 2 on both sides, I get 1 over t plus 2 is greater than 2, and therefore I have just reconstructed the expression for x, and we conclude that x is greater than 2. In part B, we are asked to hence or otherwise state the range of g. Well, what I will do is that I will go through the process of sketching the expression we just obtained for y in terms of x. I will then apply the restriction that x is greater than 2, and I'll be able to see the range of g, the output of g. So the first thing to do is substitute x is 0, and we see that when x is 0, we get that y is equal to 4 over 5. I will then substitute y is 0, so I'm finding the cuts on the axis. This leads to x minus 4 is equal to 0, and then x is 4. Now, seeing that this expression here corresponds to a reciprocal function, it means that we've got both a horizontal and a vertical asymptote. So for the asymptotes, I start by considering the value of x that will lead to division by 0. So we've got 3x minus 5 is equal to 0. Leading to x is 5 over 3, which is the equation of the vertical asymptote. And for the horizontal asymptote, I consider the behavior of y as x tends to infinity. So as x tends to infinity, the minus 4 and the negative 5 are insignificant. So this simplifies to 1 over 3. So we can see that y tends to 1 over 3, and therefore the equation of the horizontal asymptote is 1 over 3. Now, if you are not comfortable with this approach, what you can do is go on your calculator. I will substitute a really big value on my answer key, and then I will evaluate this for x, which means we've got ans minus 4 over 3 ans minus 5. So essentially, I'm substituting the big value for x into this expression, and I want to see what y would look like. If I press the answer key, I get the 1 over 3. So that's the equation of the horizontal asymptote. This means I can proceed with sketching my curve. We've got the axis here. We've got asymptotes at x is 5 over 3 and y is a third. We know we are cutting the y-axis at 4 over 5, so somewhere here. We're cutting the x-axis at 4, so somewhere here. So the graph should look something like this. And additionally, I need to apply the restriction that x is greater than 2. So I will proceed in evaluating y when x is 2. So when x is 2, I get that y is equal to 2 minus 4 over 3 times 2 minus 5, which gives an answer of negative 2. And therefore, going back to my sketch, the point 2, negative 2 is there. We need to be greater than 2. We need to be here, so I'll highlight this. So the output is anything from negative 2 up to 1 over 3, not including the boundaries. And therefore, we conclude that we've got negative 2 less than y less than a third for the range of g. In question 5, we are asked to use a substitution u is 3 plus the square root of 2x minus 1 to find the value of this integral, giving our answer in the form p plus q ln 2 with p and q being integers to be found. So let's start with the substitution we were given. We've got u is equal to 3 plus the square root of 2x minus 1. Well, we know that in integration by substitution, it's essentially a translation process. I need to translate the dx, the expression to be integrated, as well as the limits from x into u. So instead of starting to differentiate as it stands, I prefer to start by saying u minus 3 is the square root of 2x minus 1, and therefore u minus 3 squared is equal to 2x minus 1. I will now differentiate from left to right, so 2 times u minus 3 du is equal to 2 dx, and obviously the 2 with the 2 will cancel out, and I'm left with u minus 3 du is equal to dx. So I know what to replace dx with. I will then look at the limits of 1 and 13. Now when x is 1, u is equal to 3 plus the square root of 2 times 1 minus 1, and this gives an answer of 4, whereas when x is 13, we've got u is equal to 3 plus the square root of 2 times 13 minus 1, and this gives an answer of 8, which means I can proceed with the integration. So we have the integral from 1 up to 13 of 4 over 3 plus the square root of 2x minus 1. The new limits, we have found this to be 4 and 8, and we're looking at 4 over u times the u minus 3 du. Now this simplifies to the integral from 4 up to 8 of 4 minus 12 over u du, which gives me 4u minus 12 ln u from 4 up to 8. I will proceed by substituting the upper limit of 8, giving me 4 times 8 minus 12 ln of 8, and then the lower limit of 4, which is 4 times 4 minus 12 ln 4. So we're looking at 32 minus 12 ln, and I will write 8 as 2 to the power of 3, minus 16 plus 12 ln of 2 squared. So 32 minus 16 is simply 16, and the 2 to the power of 3 here, the 3 can come down, so we're looking at minus 36 ln 2 plus 24 ln 2, so we're looking at 16 minus 12 ln 2, which matches with the form that we were asked to give our answer to. So 16 minus 12 ln 2 is our final answer. In question 6, we're given the curve with this equation here, and we need to find dy dx in terms of x and y. This is the question on implicit differentiation. So we differentiate from left to right, applying all rules of differentiation as usual. If we happen to be differentiating a term in y, we put a dy dx term. So the derivative of 4y squared will be 8y dy dx. Then the derivative of 3x is of course 3. And then we need to apply the product rule of differentiation. So the derivative of 6y will be 6 dy dx, and I keep the e to the minus 2x, plus I keep the 6y, and the derivative of e to the minus 2x is minus 2e to the minus 2x. So we're looking at 8y dy dx plus the 3 is equal to 6e to the minus 2x dy dx minus 12y e to the minus 2x. Remember, we are trying to make dy dx the subject. So on the left hand side, I've got 3 plus 12y e to the minus 2x. And on the right hand side, we've got 6e to the minus 2x dy dx minus the 8y dy dx. So this leads to 3 plus 12y e to the minus 2x is equal to dy dx, which is a common factor, times 6e to the minus 2x minus 8y, and therefore 3 plus 12y e to the minus 2x, and all divided by 6e to the minus 2x minus 8y to be equal to dy dx. We now have that the curve crosses the y-axis at the origin and at the point P, and we need to find the equation of the normal to the curve at P, writing and answering in the form y is mx plus c, where m and c are constants to be found. So the equation of the curve is here. We know that we're crossing the y-axis. This simply means that x is 0. Now if I substitute x is 0 here, obviously the e to the minus 2x is e to the 0, which is 1. So this leads to 4y squared being equal to 6y, and therefore 4y squared minus 6y is 0. I will factor out the 2y, so 2y brackets 2y minus 3 is 0, leading to y being 0, or the 2y minus 3 being equal to 0. So we've got 2y is equal to 3, which means that y is 3 over 2. And therefore we conclude that the point P has coordinates 0, 3 over 2. With the other solution of y being 0, this is simply the origin. I will proceed by evaluating dy dx at this particular point. So when x is 0 and y is 3 over 2, this leads to 3 plus 12 times 3 over 2 times e to the 0 over 6 e to the 0 minus 8 times 3 over 2, which gives an answer of minus 7 over 2. And therefore, we conclude that since we're looking for the normal, I will flip and change the sign. So the gradient of the normal is 2 over 7. And we know that this straight line has a gradient of 2 over 7. It cuts the y-axis at 3 over 2. So its equation should be y is equal to 2 over 7x plus the 3 over 2. In 7a, we're asked to find the integral of e to the 2x sine x dx, and we recognize this as integration by parts. So the rule says that the integral of u dash v is uv minus the integral of uv dash. So we're looking at the integral of e to the 2x sine x dx. I will be setting u to be e to the 2x and v dash to be sine x. This means that u dash will be 2e to the 2x and v is minus cos x. So we're looking at e to the 2x times negative cos x minus the integral of 2e to the 2x times minus cos x dx. So this simplifies to minus e to the 2x cos x plus the integral of 2e to the 2x cos x dx, and we should be able to recognize the need for integration by parts again on the integral of 2e to the 2x cos x dx. This time I'm setting u to be 2e to the 2x and v dash to be cos x, leading to u dash being 4e to the 2x and v being sine x, and therefore the integral of 2e to the 2x cos x dx is equal to 2e to the 2x sine x minus the integral of 4e to the 2x sine x dx. So let's put everything together. We have the integral of e to the 2x sine x dx being equal to minus e to the 2x cos x, which is from here, plus the result we just obtained here. So we've got plus 2e to the 2x sine x minus 4 times the integral of e to the 2x sine x dx. Now we should be able to see that we've got the same integral on either side of the equation. So I will call this integral here to be capital I, and we notice that it's the same integral here. So what I'm highlighting here is also capital I, which means we can say that the capital I is minus e to the 2x cos x plus 2e to the 2x sine x minus 4i, and therefore we get that 5i is minus e to the 2x cos x plus 2e to the 2x sine x. I will divide everything by 5, leading to I being minus 1 over 5 e to the 2x cos x plus 2 over 5 e to the 2x sine x, and we also need a constant of integration because this was an indefinite integral. In part B, we are asked to find the exact area of the finite region R, shown shaded here. The equation of the curve is y is e to the 2x sine x. I will start by finding the cut on the x-axis, which I will call P. Obviously, since this is a cut on the x-axis, we know that at P, y is equal to 0, which means we're looking at e to the 2x sine x is equal to 0. Now, e to the 2x is never 0, so we need sine x to be 0. So sine x is equal to 0 is the equation we need to solve, and we know that the sine wave is 0 at 0 and every pi, so x could be 0, pi, 2 pi, and so on. We can see the first cut on the x-axis here at 0, so P corresponds to the second solution. So we know that point P has coordinates pi, 0, and therefore the area of the region R is given by the integral from 0 up to pi of e to the 2x sine x dx. The integral we just found in part A, which was minus 1 over 5 e to the 2x cos x plus 2 over 5 e to the 2x sine x, and the limits are 0 and pi. Well, let's start by substituting the upper limit. So we've got minus 1 over 5 e to the 2 pi cos of pi plus 2 over 5 e to the 2 pi sine pi, and minus the minus 1 over 5 e to the 0 cos of 0 plus 2 over 5 e to the 0 sine of 0. Well, obviously we should be able to recognize that sine of pi is 0 and sine of 0 is also 0. Cos of pi is negative 1 and cos of 0 is 1. So this leads to 1 over 5 e to the 2 pi plus 1 over 5, and therefore we're looking at e to the 2 pi plus 1 over 5 as required. In question 8, we're given two lines, L1 and L2. We're told that lambda and mu are scalar parameters, b is a constant, and we are asked to prove that for all values of b not equal to 7, the two lines are skew. Well, let's start by reminding ourselves what it means for two lines to be skew. Well, we've got three cases. Either two lines are parallel, or two lines meet at a point, or the third case is that they are skew. So they are skew if they are not parallel and if they do not meet at a point. Now, how do we check the parallel part? Well, we check the direction vectors, and if one is a multiple of the other, then we can conclude that the two lines are parallel. So looking at the direction vectors here, they would be parallel if one was a multiple of the other. Now we can see that for 2 to become a 4, I need to multiply by 2, but for negative 1 to become a negative 3, it has to be multiplied by 3. So the two direction vectors are not multiples of each other, and therefore we conclude that the two lines are not parallel, so I have ruled out the part of them being parallel. I will now investigate the possibility of them intersecting at a point, and I'll be equating their I, their J, and their K components. So I'll be doing minus 1 plus 2 lambda is 2 plus 4 mu, and so on. And these will lead to three sets of equations. So the first equation is minus 1 plus 2 lambda is equal to 2 plus 4 mu. The second equation is 5 minus lambda is negative 2 minus 3 mu. And the third equation is 4 plus 5 lambda is equal to minus 5 plus mu b. So from the first equation, we can see that 2 lambda is equal to 3 plus 4 mu. From the second equation, we arrive at 7 plus 3 mu is equal to lambda. And I can solve simultaneously here to find the values of lambda and mu. So I'll be substituting lambda with 7 plus 3 mu into the first equation. This leads to 2 times 7 plus 3 mu being equal to 3 plus 4 mu, and therefore we're looking at 14 plus 6 mu is equal to 3 plus 4 mu, and therefore 2 mu is equal to negative 11, which gives an answer for mu of minus 11 over 2. Let's proceed in finding lambda. Lambda is 7 plus 3 mu, so 7 plus 3 times minus 11 over 2, and therefore lambda is minus 19 over 2. And I will use these values for mu and lambda to determine the corresponding value for b. So we've got 4 plus 5 times the value of lambda of minus 19 over 2 being equal to negative 5 plus negative 11 over 2 times b. This leads to minus 87 over 2 being equal to minus 5 minus 11b over 2. So we get 11b over 2 being equal to 77 over 2, and therefore we conclude that b is 7. This means that for b is equal to 7, the two lines have a point of intersection, the two lines meet, and therefore for b not equal to 7, the two lines are skew. In question 9, we've got a curve described parametrically here. Theta is the parameter, it attains values greater than or equal to 0. We are told that we've got this finite region here shown shaded, bounded by the curve, the x-axis, and the line with equation x is root 3. Now we are rotating this region through a full revolution about the x-axis, forming a solid of revolution, and we need to show that the exact volume of this solid is given by this integral with p and k being constants to be found. Well, let's start by stating that the volume of revolution, capital V, is given by pi, the integral of y squared dx, and the limits are 0 up to root 3. Now we don't have the y in terms of x, we've got y in terms of theta, so this is pi, the integral of y squared dx d theta times d theta. So I also need to change the limits because 0 and root 3 refer to x limits. So when x is equal to 0, this means that tan theta, the parametric equation for x, is equal to 0, and therefore theta is 0. And when x is root 3, we get that tan of theta is root 3, and therefore theta turns out to be pi over 3. So the new limits of my integral will be 0 and pi over 3. We also have that x is equal to tan theta, and therefore dx d theta is equal to sec squared theta, and therefore we are looking at pi times the integral from 0 up to pi over 3 of 2 sine 2 theta all squared, this is the y squared, times sec squared theta d theta. So this is pi, the integral from 0 up to pi over 3 of 4, the 2 squared gives me a 4, and the sine 2 theta can be written as 2 sine theta cos theta, the double angle for sine squared, and then sec squared is 1 over cos squared theta d theta. So we are looking at pi, the integral from 0 up to pi over 3. Now the 2 sine theta cos theta all squared will give me a 4 sine squared theta cos squared theta. So the 4 times this 4 will give me 16. We've got sine squared theta, we've got cos squared theta, we've got 1 over cos squared theta d theta, and the cos squared theta terms will cancel out, so I'm left with the integral of pi 16 sine squared theta d theta. Now this is a classic example where I have to use the double angle for cosine to express sine squared in terms of cos 2 theta. We know that cos of 2 theta is equal to 1 minus 2 sine squared theta, and therefore 2 sine squared theta is 1 minus cos of 2 theta. And what I will do, I will write 16 as 8 times 2. So we're looking at 8 pi, the integral from 0 up to pi over 3 of 2 sine squared theta d theta, leading to 8 pi, the integral from 0 up to pi over 3 of 1 minus cos 2 theta d theta. And in order to match the exact form given here, I will take the 8 pi within the integral, and we are looking at the integral from 0 up to pi over 3 of 8 pi times 1 minus cos of 2 theta d theta. In part B, we need to proceed and use algebraic integration to find the exact volume of this solid of revolution. In other words, I need to evaluate the integral we obtained in part A. So the 8 pi can come out, it's a constant. The integral of 1 is theta. The integral of cos 2 theta is going to be a half sine 2 theta, and the limits are 0 and pi over 3. So this leads to 8 pi. If I substitute the upper limit, I get pi over 3 minus a half sine of 2 pi over 3. And if I substitute the lower limit, both these will be 0 and sine of 0 is 0. So we've got an overall contribution of 0 from the lower limit. So we're looking at 8 pi times pi over 3 minus root 3 over 4, which I can expand to get 8 pi squared over 3 minus 2 pi root 3. In 10a, we are asked to write 1 over h minus 5 times h plus 3 in partial fraction form. So essentially, we're looking at partial fraction decomposition. So 1 over h minus 5 times h plus 3 can be decomposed into a constant a over h minus 5 plus a constant b over h plus 3. I will get rid of the denominators by multiplying throughout by the LCM, which is h minus 5 times h plus 3, and this leads to 1 is equal to a times h plus 3 plus b times h minus 5. Now what we are looking at is an identity, which means it holds true for all values of h. I will put h to be 5 because this will eliminate this part here and will allow me to recover the value of a. So when h is equal to 5, we get that 1 is equal to a times 5 plus 3. So 1 is equal to 8a, and therefore we conclude that a is 1 over 8. And when h is negative 3, it's the other nice value for h that will eliminate the part here and will allow me to find the value of b. And this leads to 1 being equal to b times the negative 3 minus 5. So we've got 1 is minus 8b, and therefore b is minus 1 over 8. I need to write my final answer. I cannot stop at a and b. So we have arrived at 1 over h minus 5 times h plus 3 being equal to 1 over 8 over h minus 5 minus 1 over 8 over h plus 3. We're now given that the depth of water in a storage tank is being monitored. We've got that the depth of water, capital H meters, follows this differential equation. T is the time in days since the start of the monitoring. The initial depth of the water is 13 meters, and we need to solve the differential equation to arrive at this expression for capital H in terms of T. So I need to solve the differential equation. I will do this by separating the variables, which means I will use cross multiplication to collect the h with the dh term on the left hand side and the t with the dt terms on the right hand side. So we are looking at 1 over h minus 5 times h plus 3 dh being equal to minus 1 over 40 dt, and I can integrate both sides. Well, I recognize the left-hand side as what I have just decomposed into partial fractions in part A. So we're looking at 1 over 8 over h minus 5 minus 1 over 8 over h plus 3 dh being equal to the integral of minus 1 over 40 dt. Before proceeding, I've got an idea of multiplying everything by a to get rid of the fractions here. This leads to the integral of 1 over h minus 5 minus 1 over h plus 3 dh being equal to minus 8 over 40 dt, and therefore we are looking at ln of the absolute value of h minus 5 minus ln of the absolute value of h plus 3 being equal to minus 0.2t, because the 8 over 40 is simply 0.2, plus a constant of integration. Now we'll proceed by using the boundary condition that when t is 0, we get that capital H is 13 to determine the constant c. So we've got ln of the absolute value of 13 minus 5 minus ln of the absolute value of 13 plus 3 being equal to 0 plus c, and therefore we've got ln of 8 minus ln of 16 is equal to c. Obviously I can combine the two ln's because ln of 8 minus ln of 16 is ln of 8 over 16, which is a half. So ln of a half is c, which I can see as ln of 2 to the minus 1, and therefore minus ln 2 is the value of c, and therefore the general solution goes into a particular solution that says ln of the absolute value of h minus 5 minus ln of the absolute value of h plus 3 is equal to negative 0.2 t minus ln 2, and therefore I will collect all the ln's on the left hand side. We get ln of h minus 5 minus ln of h plus 3 plus ln 2 is equal to minus 0.2t. We know that when we've got addition of logarithms, we multiply, and when we've got subtraction, we divide, and therefore this leads to a ln of 2 times h minus 5 over the h plus 3 being equal to negative 0.2t, and therefore we arrive at 2h minus 10 over h plus 3 being e to the minus 0.2t. Remember, I'm trying to make capital H the subject here, so I will cross multiply to get 2h minus 10 is equal to h e to the minus 0.2t plus 3e to the minus 0.2t. I'll be collecting the h terms on the left-hand side, leading to 2h minus h e to the minus 0.2t is equal to 10 plus 3e to the minus 0.2t. And therefore, if I factor out the h on the left-hand side, I get h brackets 2 minus e to the minus 0.2t is equal to 10 plus 3e to the minus 0.2t. And therefore, we get that h is equal to 10 plus 3e to the minus 0.2t over the 2 minus e to the minus 0.2t as required. In part C, we're asked to find the time taken for the depth of the water to fall to 8 meters. I will not be substituting capital H to be 8 here. Instead, I will substitute it into this equation here. It will make easier the calculation of t. So we will be putting capital H to be 8, leading to a ln of 8 minus 5 minus a ln of 8 plus 3 plus ln 2 is equal to negative 0.2t. So we're looking at ln 3 minus ln of 11 plus ln of 2 to be negative 0.2t. Now I can evaluate the left-hand side. It gives you an answer of negative 0.6061 ... being equal to negative 0.2t. And if I divide both sides by negative 0.2, I get t to be 3.03 days, correct to 3 significant figures. Now, according to the model, the depth of the water will eventually fall to k meters, and we need to state the value of the constant k. Well, let's recall the expression we obtained for capital H. I need to consider the long-term behavior of capital H as t goes to infinity. So we know that as t goes to infinity, the e to the negative 0.2t term will go to 0. So these will vanish and these will vanish. We can see that h tends to 10 over 2, which is obviously 5. And therefore we conclude that k is equal to 5. If you do not want to go through the process of considering the long-term behavior analytically like we did here, we can go on the calculator. I'll put like a big number like 10,000 on my answer key, and I will evaluate this. So 10 plus 3, and we've got e to the minus 0.2 ans. So I'm replacing the expression for capital H with t replaced with a really big value. So in the denominator is 2 minus e to the minus 0.2 answer key, and this gives the answer of 5, confirming that k is equal to 5.